In this video, we're going to be talking about column chromatography and the use of partition ratio as a measure of your ability to separate a mixture. We had previously talked about the fact that separation of a mixture could be done in an organic separatory funnel by placing the mixture of A and B into a sep funnel. You would allow those to come to some equilibrium based on their solubilities in a polar and nonpolar solvent. Of course, this became somewhat complex because in order to do a more purification, you had to use multiple sep funnels and multiple equilibria. This process was mechanized using the Craig countercurrent experiment, which is the equivalent of doing many sep funnels or many equilibria to achieve a separation between the compounds. This process can also be duplicated in what is referred to as column chromatography, in which case you don't have individual separate separatory funnels. You have a column which has a stationary phase, so in this cross section it might be the interior surface of the column, and you have a mobile phase which moves through the column. In this case, A and B can interact with the surface and come to equilibria between the moving phase, the aqueous phase, and the stationary nonpolar phase. The process of column chromatography is illustrated in this diagram, in which case you have your stationary phase in the column and you place your mixture on the top of that column. You can then pour a mobile phase on top of that mixture, and if the compound has a greater affinity for the stationary phase, so if it has a greater affinity for the stationary phase, it will stick to the stationary phase. If it has a greater affinity for the mobile phase, it will actually wash through first, following the mobile phase as it goes through the column. In this way, the compound which has the greater affinity for the mobile phase will be washed off the column first, and the compound that has the greater affinity for the stationary phase will be washed off the column later. This gives rise to what we refer to as a chromatogram. The time that it takes for a compound to come off is referred to as the retention time, and the retention time is in fact directly proportional to its affinity for the stationary phase. If it has a great affinity for the stationary phase, then it's going to take a longer time for it to be washed off the column. In the separatory flask, we described its affinity for the upper phase as its distribution coefficient. And it's the difference in distribution coefficients that allows you to separate compounds in a separatory funnel. The distribution coefficient refers to the upper phase in the sep funnel as opposed to the concentration in the lower phase. This really has no meaning in column chromatography because there is no upper and lower, but we can refer to it now as the stationary phase and the mobile phase. So the equivalent of the distribution coefficient when we go to column chromatography is the partition coefficient, and it is defined as the total concentration in the stationary phase divided by the total concentration in the mobile phase. This too then, the partition coefficient, is a measure of a compound's affinity for the stationary phase. The higher the affinity for the stationary phase, the bigger the partition coefficient is. It is important to note that concentration, like molarity, moles per liter, depends upon the amount of the solution or the volume that you're talking about. If you want to go just to specific amounts of things, like moles of things, then you have to multiply concentration times the volume. And that's what we do when we talk about actually a more useful unit called the partition ratio, K prime. Partition coefficient is based on concentration. Partition ratio is truly the amount in the stationary phase divided by the amount in the mobile phase. And you can achieve that by multiplying the concentration times the volume, sort of like taking molarity times volume gives you moles. Concentration times volume gives you amount. So, if you have the partition ratio, which is an amount-based unit, it is the concentration times the volume. Or we can simply write that as K prime, the partition ratio, is the partition coefficient times some volumetric ratio. That converts partition coefficient into an amount-based partition ratio. This volumetric ratio is given the symbol beta, and it is the volume of the stationary phase divided by the volume of the mobile phase. So the partition ratio K prime becomes K times beta. As we discussed earlier, the retention time of a compound is directly proportional to its affinity for the stationary phase, as is the partition ratio. So the retention time, the amount of time that it takes for a compound to come off the column, is the same thing or related to the partition ratio. Partition ratio is high when once it's attracted to the stationary phase. Retention time is longer when it's attracted to the stationary phase. Ultimately, the time that a compound spends on the column is going to be the amount of time it spends in the mobile phase plus the amount of time it spends in the stationary phase. The total retention time, that is the time when you start to the time when a compound comes off, has to be the sum of the time spent in the mobile phase and the time spent in the stationary phase. K prime can therefore be calculated as time in stationary phase divided by time in mobile phase. And that's really calculated by taking the total retention time minus the time that it takes for a mobile phase to get off the column. This is called the adjusted retention time, or T prime R. T prime R is the amount of time that a compound stays in the stationary phase. If you put something on the column, how much time is it actually stuck to the stationary phase? That's what T prime R is. K prime, the partition ratio, which is what separation is based on, can be calculated as the adjusted retention time divided by the time spent in the mobile phase, or the time for an unretained compound. We can calculate this based on a compound having a total retention time of 1.27 minutes if the flow rate of the mobile phase is 37 milliliters per second in a column having 1.0 liters. If the flow rate is 37 milliliters per minute, that means 1.70 liters divided by its flow rate means it's going to take about half a minute for that mobile phase just to travel through that 1 liter. The time spent for the mobile phase from start as it flows through the column, if it's flowing at 37 milliliters per second, it's going to take 27 seconds for a molecule of the mobile phase to simply exit that volume. That is the time of the mobile phase. We can then calculate K prime, 1.27 minutes minus 0.45 minutes divided by 0.45 minutes gives us a partition ratio of 1.82. Remember, that value is its affinity for the stationary phase. If something has a larger or smaller K prime value, that will affect its retention time on the chromatographic column.